Hello everyone. Today we are going to learn about the matrix, what they are, what their types, and where they are used. Matrices are foundational in many areas of mathematics and applied science. So let's dive in. Okay. So what's the matrix? Matrix is just a number of numbers arranged in rows and columns. It's like a spreadsheet, but for math. The size or dimension of a matrix is written as m into n, where is m is row and n is column. For example, 3 into 3 matrix has 3 rows and 3 columns. Matrices are used everywhere in computer graphics for things like rotating images and machine learning handled to data sheets, and engineering and physics for modeling real world systems. Let's move to next slide. Okay, this slide is about the types of matrix. There are many different types of matrix. The square matrix has the same number of rows and columns. Row matrix just one row, while column matrix has just one column. Zero matrix has only zeros in all positions. Diagonal matrix has numbers only on its main diagonal. Scalar matrix is diagonal matrix where all diagonal values are the same. And identity matrix has ones on diagonal and zeros elsewhere. Let's move into the next slide. Okay, this slide is about the symmetric and skew symmetric matrix. These matrix are two special type of square matrix. Symmetrical matrix is one that looks the same when flipped across the diagonal. It equals its own transpose. A skewed symmetric matrix is the opposite, flipping its every number the negative of what it was. Also, the diagonal entries in skewed symmetric matrix are always zero. These types show up in physics, optimization, and even machine learning. Okay, now let's talk about the matrix operation. Let's look what we can do with the matrix. We can add or subtract them if they're the same size. Just add the numbers in matching positions. Scalar multiplication means multiplying every element in the matrix by the same number. Matrix multiplication is more complex. It combines rows from the first matrix with columns from the second using dot products. This operation are how we solve the equation and manipulate the data with matrix. Okay, this slide is about the determinant and inverse matrix. Now let's talk about the determinant. This is a single number calculated from a square matrix. It tells us the things like whether the matrix is invertible. If the determinant is zero, the matrix has no inverse. The inverse of a matrix is like dividing. It undoes what the matrix does. But remember, not all the matrices have inverses. For 2 into 2 matrix, the inverse formula is pretty simple, using the determinant and switching some values and around. And my last part is about the eigenvalues and the eigenvectors. This is a powerful concept of eigenvalues and eigenvectors. An eigenvector of a matrix is the direction that doesn't change when the matrix acts on it. It might scratch or shrink, but it doesn't rotate. Eigenvalue is much. Eigenvalue is how much the stretch or shrink. This concept is used in machine learning, in physics, even in structural engineering. Now this part named application of metrics will be presented by Sabik Ahmed.
Hello everyone, my name is Sabik Ahmed and today I will give you a quick overview of the application of matrices. To true matrices might seem like abstract math tools, and at first they actually play critical roles in many real-world applications, from engineering to data science. Let's begin with transformations. In graphics, matrices are used to rotate, scale, and move objects in both 2D and 3D space. Every point in an object is transformed by multiplying with a matrix. In 3D rendering, especially in game engines, transformation matrices help simulate lighting, perspective, and animations. This makes scenes look realistic and dynamic in real life. In circuit analysis, matrices help solve large systems of equations using Kirchhoff's laws, making it easier to analyze voltage and currents in complex electrical networks. In quantum mechanics, the behavior of quantum states is described using matrices. Operators like the Hamiltonian, which dictate energy and evolution of states, are matrix based. In structural engineering, especially in finite element analysis, engineers use stiffness matrices to model how buildings and machines react to forces. This ensures safety and structural integrity. In data science, matrices represent datasets. Rows usually indicate samples and columns indicate features. In format, this format makes statistical analysis and machine learning computations efficient. In recommendation systems like Netflix or Spotify, matrices model user interactions with content. By factorizing these matrices, we can uncover hidden patterns and suggest new items to users. Matrices also used in population modeling. A good example is the lazy matrix, which helps to predict changes in population based on birth and survival rates across age groups. By repeatedly multiplying these matrices with a population vector, we can forecast future population trends. This is useful in ecology, public health, and demography.
Now, this part will be provided by Abrar Enan.
One. Hello everyone, this is Shaidul Enan. Today we will discuss about image processing by matrix. Image processing refers to performing operations on images to enhance or extract information. Image processing treats image as matrix of pixel values. Each pixel brightness or color is a number in the matrix. Operations like filtering, blurring, and edge detection use matrix math. By manipulating these metrics, we can enhance or analyze image. Digital images are stored as metrics of pixel values. It is widely used in photography, medical imaging, satellite imaging, and computer vision. Image brightening. Image brightening increases the intensity of an image, making it appear lighter. In digital image, pixel values range from 0 to 255 for 8-bit image. Brightness is increased by adding a constant value to all pixels. New pixel equal original pixel plus brightness offset. Blurring. Blurring is a technique used to reduce noise or detail in an image. This is done using convolution, where a small matrix called a kernel is moved over the matrix and each pixel is updated based on the values of its neighbor. Here we can see blurring kernel matrix. This matrix is convoluted with the image to reduce sharp transitions. Larger kernels produce stronger blurry effects. Edge detection. Edge detection highlights place in an image where there is a sudden change in intensity or color, usually indicating object boundaries or texture changes. This is achieved by applying convolution with special matrix called edge detection kernels. Sober operations are convolution matrices that highlight changes in pixel intensity. They detect edges by finding gradients in the image. There are two sober kernels, one for horizontal changes and one for vertical changes. 3x3 sober matrix compute intensity gradient in both directions. These gradients were then combined to highlight the edges, especially the tree outline, leaves, and background features. Also, we can use metrics for face detection and recognition, medical image analysis, object tracking in video, artistic filters in photography apps, etc. Thank you.
And thank you, Jahaz sir, to provide of of thank you, Jahaz sir, to provide to our group to give a wonderful presentation.